Okay, what else? Did we finish our examples? Did you finish your web work? Anything else you would like to see worked? Do I have some examples still hanging? It's like I wasn't even here on Friday. I don't know what I did. You have no idea what I did.
I think of that like final example on
There's one more example to go.
the problem you'll say.
Oh, yeah, we need to finish that.
Okay, let's finish it. And if you guys think of more web work, we can do more web work. Otherwise, I'm prepared to go on to new and exciting things.
Next.
We're gonna go polar coordinates.
I'm not a physics major.
All you do is whine, is whine.
Hey, let me recall that rec letter and make a few changes. Down. Okay, so I have another example, put somewhere here. This is very crowded little classroom up here. The entire last one, or are we going about the line X is 1? There's number 8 on our handout of examples. Number 8 on our examples handout. Okay. So we're going to draw a parabola y is equal to x squared. The line y is equal to 3 minus 2x and the x-axis, and see what region is bounded by those. So I'll make kind of a big picture. 3 minus 2x crosses the y-axis at y is equal to 3. Crosses the x-axis at x is 1.5. Then that's a parabola through the origin. And then the x-axis. So we're talking about this little triangular piece down here that bounds the region. So it looks like it goes through 0, 0, 1, 3 halves, 0. And I think we decided they intersected at 1, 1. When x is 1, y is 1. When x is 1, y is 1. And because this region has that sharp corner right there, it's simple in terms of the variable y. If you want to do anything with the variable x, then you got to use 2 integrals. So with that in mind, I'm going to try to do everything as a dy problem. All of my rotations I'm going to do with partitioning elements parallel to the x-axis. Just because that makes 1 integral as opposed to 2. Now we're going to do some 3 different revolvings. Well, first in part A, I'm going to revolve about the x-axis. So if my partitioning element is parallel to the axis that it's going around, what shape will be made by that partitioning element? Shell. Now the x-axis, we're going to use shells. And our plan with shells is the 2 pi RH times the thickness goes in our integral. The thickness is either dx or dy, and our picture is telling us it's dy. So everything that I put in here, the r and the h, has to be as functions in the variable y. Let's put the 2 pi out here. Now, when that shell is formed, the h comes from taking the graph on the right minus the graph on the left. So I'm going to take those 2 equations and write them as x is equal to blah, 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 y. So starting with this one, this graph is x is equal to the positive square root of y. This one, if I swap places here, I get 2x is 3 minus y, so x is 3 minus y divided by 2. X is 3 minus y divided by 2. And that graph, the line is on the left, the parabola is on the right, so h is 3 minus y over 2 minus the square root of y. That's going to be the h. R is the distance between the axis of revolution and the middle of any partitioning rectangle. So as that rectangle moves up the region, R is going to be this distance right here. How can we measure that distance from the x-axis if it grows throughout the problem?
With y.
That's the variable y. It's going up the y-axis. So R is just the variable y. And so when we fill that in, there's the 2 pi. R is y. H is right graph minus left graph. And then we've got the dy. And then the numbers on the integral sign are the y values throughout the region. Give me smallest to largest. 0 to 1. Are you happy with that?
Yep. Feels right.
All right, we're just setting them up. All right, now let's change our rotating axis to be the y-axis. Keep the rectangle that way, and in part B, we're going about the y-axis. And so if our partitioning element is perpendicular to the axis of revolution, what shape is constructed here? Washer. We're going to get washers. In the method of washers, our plan is pi times the outer radius squared minus the inner radius squared times the thickness. In all 3 parts, our thickness is going to be dy because I'm not changing the orientation of the partitioning element. So here's the pi, and there's the dy. We just got to figure out what the 2 radii are going to be. So let me go over here. We're taking that thing. Here's the y-axis. Here's our partitioning element. And it's going to come out here and give us this little shape like that. And then the circle here. So my outer radius is going to be from the axis of revolution to the furthest extent in my graph. So from the axis of revolution to the linear function. And then the thing that generates the hole in it is the leftmost box, and that's the parabola. Linear function minus parabola. Linear function's big R, parabola is little r. But we've got to have them in the reorganized way. The line was this one, that's going to be my big R. And the parabola was that one, so that's little r. So big R is 3 minus y over 2. Little r is square root of y. And fill them in here. There's the pi. Big R is 3 minus y over 2. And little r is the square root of y. And I get the range on the y's are still the same, 0 to 1. Can you see why I chose those in that order? Okay. Now, in the third part, we're going to take that region and we're going to revolve it about a non-axis. We're going to swing it over about x is equal to -1. So here's Here's the y-axis. Here's the line x is equal to -1. And then we've got our graph. We've got the parabola and the line. And our partitioning element is still perpendicular to the axis of revolution. So the plan was as it was in part B. Perpendicular gives you washers, parallel gives you shell. Okay. So we're going to get washers. So we're going to integrate pi big R squared minus little r squared, and our thickness is dy. So again, that swings around here. The big R is going to come from here to there. And the little r goes from here to there. So I've gone the same kind of distance, but 1 unit more. So do you agree if I just add 1 to each of these, I have the big R and the little r?
Yeah.
I've gone 1 unit further than I did in the last example. And so here, big R is the linear function, 3 minus y over 2 with 1 more unit of distance. And the little r is square root of y with 1 more unit of distance. So we put those in here. Here's the pi. This is still 0 to 1. Big R, 3 minus y over 2 plus 1 squared. Little r is square root of y plus 1 squared dy. So I've got room for some what if questions. So my first what if question is, what if I moved my axis of revolution? So let's make this part D. What if this were my axis of revolution? That was at x is 1/3. Yes.
So referentially, it would switch the positions of 3 minus y over 2 into square root of y
Correct.
plus 1. And instead of plus 1, it would be 1 minus
Close.
square root of y. Oh, 1/3. sorry.
1/3 minus
Yeah,
that, because
1/3.
I'm measuring from
Don't know why I said
the
that.
axis of revolution, which is the line x is 1/3. And to get my big R now, do I have another color? No, I don't. To get the big R, you need to go back from the axis of revolution to the tip of the rectangle. So if this is 1/3, and if this is square root of y, that's 1/3 minus square root of y. And then if this is the 3 minus y over 2, to get the little r, we take 1/3 minus that. And everything else is the same, 0 to 1, 0 to 1. So that's our part B. Does that make sense to everybody? So if I added a part E and revolved things about a line through here, redraw that. What was that? That's line y is equal to 1. And here's the y-axis, here's the x-axis, parabola, line, and the partitioning element here is parallel to the axis of revolution. Have I changed how long that partitioning element is by moving the axis of revolution? Still right graph minus left graph.
Just affected R.
Just affecting R, because now my axis of revolution. Before, when we came about this axis, we used that as R, and we said that was the variable y. Now this is gonna be R. It's always measured to the axis of revolution. So what would you write as our radius? 1 minus y, perfect. So we get 2 pi r h. H is still right graph minus left graph. Okay? Everybody? If I moved it down here, then I would have added 1 to the y, or added whatever number to the y. Same thing over there. If I move my axis here, we add 1, here we subtract from the line, because the line is on the right now. But the radius in every case is measured from the axis of revolution. Any of those make you think of any more web work you wanted to ask about?
Definitely made me understand the web work a bit better, because there were some problems I just kind of brute forced and made it work.
Made it work. How do you know you make it work? You get the right answer?
Yeah, because I got the right answer.
Oh,
Gives you congratulations.
oh, the little green square. Did you find one?
Problem 10.
Problem 10. All right, let me rub out some room here. Let me rub it off from here.
Ooh, I know how to do things. Can I look it?
You want to work it? Are you gonna whine?
Oh, boy.
I need to prove myself.
You need redemption from earlier.
Yeah.
Can you work it without looking at anything?
Probably.
But we're gonna use her formulas. They might be alphabet, but it's,
So find the volume of a solid obtained by rotating the region enclosed by y is equal to x squared and y is equal to 5x. About the line y is equal to 25 using the method of discs or washers.
is it first quadrant portion or the entire, oh, it's gonna be cut off. Okay, so we're good.
Okay.
No whining. If he whines, you're welcome to throw anything you want at him.
I will help you with
Right here.
mechanical.
Anybody want this?
That is very fair.
It's full. You can throw this at him.
That feels like
I
a
throw my
salt
computer, but I
charge.
also need it, so.
You will never throw your computer. That is not allowed.
Hey, okay.
All right, parabola line.
I'm gonna make this graph. And like, I'm just gonna do the right side because the left side doesn't really come into play.
Correct.
Okay, that's x squared, and then you have y equals 5x. It intersects at 525.
We agree that it intersects at 525?
I just heard.
Okay.
Seems probable.
And now we're gonna revolve that about the line y is equal to 25.
Yes, so we got, it's
Good.
gonna be a nice little disc,
Good.
so.
Well, it says we have to use the
Perpendicular,
disc or washer. So which way is the partitioning element going?
it's gonna be perpendicular.
Perpendicular. So we going dx or dy?
Yes.
Good. Okay.
You're doing a good job, Case.
I always do a good job. When have I not done a good job?
But we don't talk about that. That didn't happen.
Okay. So everything's gonna be x. Disk is pi, outer radius squared minus inner radius squared dx.
Yes. Oh, it's
Okay.
gonna be a washer.
A washer, same
Yeah.
difference.
Okay, so we got r squared, which is, r squared is just x squared, right?
But the
Yes.
line
Big
is
R,
moved
big
up
R, I
there.
mean big R, yeah, yeah.
The line is moved.
Okay, so,
So from the axis of revolution.
oh, it's 25 minus,
25 minus whatever that equation is.
this is not doing too hot.
Grab another marker behind you, there's a whole pile of them.
School really needs to up their game on like marker provision.
Marker provision.
Okay, so big R is equal to 25 minus, goes all the way down to x squared. And then little r is 25 minus the top function,
Which
which is 5x.
Good.
Okay, so we'll take our, go over here, take the integral. This is from 0 to 5.
Because we're following the x's. 0 to 5, big R squared,
Big R squared is 25 minus, oh, we got the 9 front. I'm just gonna go ahead and put move 5.
psi outside's good.
25 minus x squared squared
big R squared minus little r squared.
25 minus 5x squared. Squared. And then
Good,
we work that
just
out.
5x squared. 5x, not the square.
Oh, right, yeah.
So 25 minus x squared, quantity squared, minus the quantity, 25 minus 5x all squared, dx.
And I think whenever I did this, I like moved it all out.
You will have to multiply it
Yeah,
out.
I factored it.
You'll have to
Does somebody
multiply
wanna
it
tell
all
me what the
out,
factor
gather
is?
like terms, and then integrate term by term. So just make sure when you multiply that out, you multiply it out as a binomial. You don't just square the first term and square the last term. That's the old freshman theorem, right? Multiply with itself and get all three terms. Thank you.
Yeah.
Is that enough?
Yes.
Is that good enough? Does anybody see why the 25 is minus the graph?
Yeah.
Polar coordinates?
I always.
You ready for polar coordinates?
Oh, I'm ready.
You're so ready?
So ready.
Okay. So we're not going to cut things up into rectangles anymore. We're not cutting anything up into rectangles when we're in polar coordinates. Polar coordinates describes the XY plane to be broken up by a ray. Take a ray, a directed line segment, and put its initial point on the origin. In polar coordinates, the origin is called the pole. Take that ray and rotate it clockwise or counterclockwise. But as that ray rotates, it can get longer and shorter. Now imagine that at the end of the ray, there's some sort of pencil. So as it gets longer or shorter, it's tracing out a graph. And the location of any point on that graph is given by an ordered pair. How long the ray is from the origin through that point, and what angle that ray makes with the positive x-axis. So ordered pairs are going to be marked with r as the first coordinate, theta was the second coordinate. So I'm going to erase everything and try to draw that. So what I want you to imagine is like if you were to watch the weather radar. The weather radar used to have these little rays that just went around and then you'd see where the clouds and showers were. That's the way things are traced out in polar coordinates. With juicy marker maybe. Can't possibly be juicy. Okay, so section 6.3. Polar coordinates. Here's the XY plane, and I'm just drawing that as a reference for you. Really, we need this, that's the pole, and then a ray of some length r. That's as far as that wants to go. Make a ray of some length r. Right now it's that length. And it makes an angle of theta with the positive x-axis. Now it's hooked at the origin, has a pencil on the end, and it's going to rotate around and trace out some sort of graph. And the equation of that graph is r is some function of theta. And the ordered pair anywhere on the graph is given by how long r is and what angle is formed. So you can just use a little bit of trigonometry and see the relationship between r in theta in polar coordinates and x and y in rectangular coordinates. If I drop a perpendicular segment down here, this height is y and that is x. So tell me how r is related to those two variables.
The hypotenuse of triangle formed.
Okay.
x-axis.
So I know that r squared is x squared plus y squared. Then we can use that angle theta to get relationships between theta, r, and x and y. For instance, the tangent of angle theta is that y value divided by x. The cosine of that angle theta is the adjacent side divided by the hypotenuse. So the cosine of that angle theta is x over r, which means x is r times cosine of theta. Y is going to be involved with the angle theta using the sine function, because the sine is opposite over hypotenuse. The sine of angle theta then is y over r. Solve that for y, and you get y is equal to r sine of theta. Where x and y both satisfy x squared plus y squared is r squared. So for instance, plot a point where r is 3 and theta is pi over 6. R is 3, theta is pi over 6 is where? You have an idea? Let's say that's 1 unit.
Would it be in quadrant 1?
Be in quadrant 1. I got to go up pi over 6. This is pi halves here. So 1/3 of that arc puts me at about right here. So that's a length of 1. There's another one. There's another one. So there's that ordered pair. But that has the same point as, for instance, r is equal to 3, theta is equal to 13 pi over 6. Because pi over 6 plus 2 pi takes me to the exact same spot. Or if I add another 2 pi, it could be the same as the ordered pair 3 and 25 pi over 6. Or if I multiply, or if I rotate my ray clockwise, I can land in that same spot as well. What's the negative angle that takes me from this particular ray to here? Or from the x-axis, sorry, to where that ray is. Give me another name for this point, but where theta is negative. I like negative 11 pi over 6, because this distance is pi over 6. All the way back around is 2 pi. So if I back up, I'm at negative 11 pi over 6. And then again, I could rename this by keep taking away multiples of 2 pi. So in the coordinate plane, xy plane, each point is uniquely designated. In the r theta plane, there are an infinite number of ways to locate the coordinates of one particular point. And to make it more interesting, I can think of this as the positive axis of a ray of angle measure pi over 6. If I extend this back into the third quadrant, then I can say that this would be part of that axis. Can you tell me the angle whose measure takes me from the positive x-axis back to a point here in the third quadrant?
7 pi over 6.
7 pi over 6. Pi over 6 more than pi. So if theta is pi over 6, 7 pi over 6, I project back by saying that r now is at negative 3 if theta is 7 pi over 6. So that's another way to name this one little point right here. Or let's find the name of that point where both r and theta are negative. and theta is between 0 and 2 pi. So tell me what the measure of the angle is from here, positive x-axis, to here in a clockwise direction. Good, -5 pi over 6. From here to here is -pi. Take off a pi over 6, we're at -5 pi over 6. Puts me on this ray. Then go back 3 units and you're at that same point. So yet another name is -3, -5 pi over 6. There are an infinite number of ways to designate one particular point. There's one and only one way to denote that in rectangular coordinates. So what I want you to find out now is for that point, what are the rectangular coordinates? Convert from these polar coordinates into rectangular and tell me what x and y are there using this information here. Got it already?
Yeah, so x would be equal to 3 cosine pi over 6. And then y would be equal to 3 sine pi over 6.
Perfect. Almost perfect, because I know what sine and cosine of pi over 6 are, so I'm going to shame you into remembering those.
3/2 and 3/2.
Okay, say that slower for the slower to hear.
Is the x 3/2 and the y is 3/2?
So wait a minute. Like
Like if
3/2, can I just say a half?
Oh, well. I think so.
Yeah, cosine of pi over 6 is square root of 3/2. Sine of pi over 6 is a half. So that ordered pair in rectangular coordinates. Cosine is square root of 3/2, so 3 square root of 3/2. Sine of pi over 6 is a half, times 3 gives us 3 halves. And that's the only way you can name that point in rectangular coordinates. Okay, so we just filled in r and theta right here to convert to rectangular coordinates. So now let's go the other way. In the xy plane, I'd like you to plot the point -2, +2. Plot the point x is -2, y is +2, and let's find 4 different ways to name that point in polar coordinates. Where both r and theta are positive, where r is positive, theta is negative, where r is negative, theta is positive, and where they're both positive. So in this example, we're going to plot x, y equal to -2, 2, and then we're going to convert to polar coordinates. In each of the following ways. I want r and theta positive. I want r negative, theta positive. I want r positive, theta negative. And then I want r negative, theta negative. Does that sound like fun?
Yes.
We're here. This calculus stuff is a good time. Which quadrant is the point 2, -2 in? -2, 2 is the one I meant to say.
Yeah.
That was a trick question.
Yeah.
Second.
Don't listen to what I say, listen to what I mean to say. I know, you sound like my husband, just listening to what I say? No. You can listen to what I mean to say, what I feel, what I'm thinking. We're in quadrant 2. right there. I want you to do first to tell me how long that ray is.
Square root
We're like square root of 8 for the length of that ray. Because if I make a right triangle by dropping down the perpendicular segment, I go back to up to x squared plus y squared is r squared. So -2 squared plus 2 squared gives me 8. R squared is 8, gives us r is the square root of 8. Okay, so that'll give us the first case where r is positive. Now we need to know an angle measured from the positive x-axis to get me to this point right here. We can use a reference angle. If you find me the reference angle, then we can convert it to a quadrant 2 angle. 3 pi over 4 is correct because,
tangent inverse is -1.
yeah, y over x is essentially 1 if I ignore the signs. Tangent is 1 at pi over 4. So to get me here in quadrant 2, I take pi over 4 away from pi, and we're at 3 pi over 4. So what did we just say? The tangent of angle theta is is y over x. And the tangent is -1 in quadrant 2 at 3 pi over 4. So r and theta are positive, corresponds to the ordered pair square root of 8, 3 pi over 4. All right, so r is negative on the extension of this axis. And so if I want theta to be positive, now I need you to think what this angle is.
Pi over 4.
Smaller, it's pi over 4 short of being 2 pi.
Yeah, 7 pi over 4.
7 pi over 4. Yes, I thought you said 10 pi over 4. That is 7 pi over 4 because 2 pi is 8 pi over 4, right? Fun with fractions. 2 pi is 8/4 pi. Take a pi over 4 away. So theta is positive 7 pi over 4. That takes us to that little black dotted line. Now go negative square root of 8 to project us back in the opposite quadrant. Good? Okay, for the next one, keep r positive, so keep r at the square root of 8, but then to get theta negative, we've got to measure this angle. I'm going to go from the positive x-axis. I'm now at pi, and then one more pi over 4. But negative. Negative pi, back another pi over 4. How much? That's too far. 5 pi over 4.
All right. Yeah.
Negative pi is 4/4, minus 1/4 is a negative 5 pi over 4. So theta is negative 5 pi over 4, takes me to that solid black ray. So it has a length of square root of 8. Now how are we going to get r negative and theta negative? Yeah, we just go to here, to the dotted part of that line, negative pi over 4, and then flip it back by making r negative. So negative square root of 8, negative pi over 4. Everybody comprendez-vous? Si. Jawohl. Anybody want to ask anything? More examples.
Like, I kind of got it, but I'm just gonna practice.
Okay, do you want to go rectangular to polar, polar to rectangular, rectangular to polar? Okay, okay, let me see, I picked the easy one, I picked where X is Y, so that you would know that it was pi over 4. How about, hmm. Okay, let's go with this point. We already did a quadrant 2, so let's do the same. For our rectangular coordinates x, y to be positive 5 square root of 3 over 2 and a negative 5 halves. So the easy one to get is R first. Positive to negative. X squared plus y squared is R squared. Same instructions, convert to polar coordinates in each of the 4 ways. Anybody have an R that we can check? 5. 5? When I square 5 squared to 3 over 2, I square each of the terms, so I get 25 times 3 over 4. That's 75 over 4. Square that and I get 25 over 4. 75 over 4 plus 25 over 4 is 100 over 4, which is 25. R is positive 5, will be a good starting point for us. Pull this off. And this. Let's see if R is positive and theta is positive in our ordered pair R comma theta. I'll put my 5 right here. Now, use right triangle trigonometry where the horizontal leg is 5 square root of 3 over 2 and the vertical leg is 5 halves. Give me a reference angle and then we can figure out how to get that angle. So if I just drew that 5 square root of 3 over 2 here and 5 halves here, let's get this angle.
5 over 6.
Tangent is y over x. So the 5 halves top and bottom will cancel, leaving us with 1 over root 3. Right, 5 halves here, 5 halves there, cancel. So tangent of theta is 1 over root 3, which comes from a ratio of sine to cosine in the unit circle of 1/2, nope, sorry, square root of 3 over 2 divided by Nope, not that way, the other way. I need the 1/2 on top and then the square root of 3/2 on the bottom. Right, does that reduce to 1/3? So I need to know what angle sine is 1/2.
It would be -5/6.
In this particular example, this theta is pi/6, so I'll build back. That's this angle. How's your trig, everybody?
30 degrees.
It's 30 degrees.
That's fine.
In calculus, we're in radians. So if you go from, get your 30 degrees and go back. Now, to get R positive, use that pi/6 as your reference angle and rotate your ray counterclockwise until it lands there. So it's pi/6 short of being 2 pi.
11 pi/6.
11 pi/6. 2 pi minus pi/6. Okay, now I want theta positive, so keep theta at an R negative, so I can't keep either number. R negative, that'll be a -5. What angle theta am I looking for? Here's the negative of that axis. What angle is this one?
5/6.
Because it is pi/6 short of being pi. Pi minus pi/6 is 5 pi/6. So that would make theta positive. We'll let you get the other two yourself. Keep working, then I'll come fill it in. Enough time? Mom? Maybe? Anybody else still calculating, or can I jump in? Go ahead. Okay, to get R positive and theta negative. So theta negative would be this way. Pi/6 short of 2 pi. Or we're going theta negative, so it's just -pi/6, right? It's already acute. -pi/6. R positive is the +5. R negative would be -5. So now go to theta is -pi/6. Project it back to that dotted line. Measure this way. -7 pi/6, because that's -pi and 1/6 more in that negative direction. So -7 pi/6. Okay. All right, for the most part, we're going to talk about our ordered pairs where both coordinates are positive. But every now and then when we're graphing something, we're going to need to find out what it means when R is negative. Speaking of graphing, when you first learned how to graph things way back when you were 7th graders in algebra and you were graphing lines, you would just take that equation and plot a million points and connect the dots. And eventually you got to where, dadgummit, that's a line, all I need to do is plot 2 points and I got it. Same thing with parabolas. You'd connect all these little goofy dots and maybe it looked like a parabola, maybe it didn't. But you know now that if you see y is equal to x squared, you got a parabola. you probably need to only plot the vertex and fake the rest. We need to get that good at graphing polar equations. For example, if I said graph theta is pi over 4, well, then I'm not discussing just an angle. Just like in rectangular coordinates, if I said graph x is 5, I'm not telling you just put a dot on the paper. X is 5 is a line. So is theta is equal to pi over 4. Theta is equal to pi over 4 is the line y is equal to x, right? Because that occurs when tangent has the same numerator and denominator. So lines in polar coordinates have as their equations, theta is equal to something. Theta is equal to an angle is the equation of a line. So we'll get to know these graphs. All right, so theta is equal to some sort of angle. For instance, what do you think this graph is? R is equal to 2.
It'll just be a line in code.
What's R do? R is a fixed ray that rotates around the pole. So take a fixed ray and rotate it around the pole, and what are you going to get? That's a circle centered at the origin of radius 2. Right? R is 2. If you square both sides, you get R squared is 4, but R squared is x squared plus y squared. So I'm going to give you equations of circles. We'll plot points like we were back in 7th grade, and then we're going to recognize that gives us a circle, and then we're going to memorize that equation. Then we're going to we'll have circles. We'll have things called cardioids. We'll have not quite a cardioid. It'll be like a lima bean, or have the big indentation, have a little indentation. Sometimes our lima bean will have a loop inside of it. We'll have infinity symbols. Those have a name. And then we have some that have lots of petals. We'll graph those. Doesn't look that ugly. It'll be prettier. So we're going to do some graphing next time. So go back and review where your angles are in the unit circle. Because we're going to be plotting around the circle instead of in rectangular coordinates. I went pretty fast. That went pretty fast. Questions for anybody at home? How did we get the R where? In the previous example there? You guys give me papers? Oh, I figured it out. Okay, thank you. All right, any other questions in the other room or?